Hello, today I will be presenting my model and some of my research to answer the question, what is the connection between carbon compounds and greenhouse gases, and how can these greenhouse gases, specifically carbon dioxide, be sorted, permanently stored, and turned into harmless compounds? This presentation will focus specifically on how to sort carbon dioxide. To start off, I must give you the context of this research and why it matters. Upwards of 150 species go extinct every day. Millions of people are displaced by extreme weather patterns caused by climate change, and 1 in 10 people per year die globally due to air pollution. As we allow excessive amounts of greenhouse gases to flood our atmosphere every day, the world we once knew is slipping away. However, one thing is common among many of these gases in our atmosphere. They are carbon-based. In fact, the most prevalent greenhouse gas, carbon dioxide, is carbon-based. Therefore, figuring out what properties of carbon make it commonly form greenhouse gases and how to remove specifically carbon dioxide from our atmosphere is crucial to saving not only our environment, but the human species as well. Now, let me explain to you the mechanism of the 3 primary carbon capture methods. Okay, chemical absorption. First, flue gas, or the gas mixture produced by burning fuel, is fed into the bottom of an absorber tower at approximately 50 degrees Celsius, while an amine and water solution is fed into the top of the tower and flows down. Amines refers to a group of organic compounds that contain carbon-nitrogen bonds. Next, when the flue gas dissolves into the solution, amines only bind to carbon dioxide. Also, carbon dioxide, specifically in the gas mixture, has a very high partial pressure, and pressure of gases and solubility have a direct relationship, so most of it will dissolve. Beyond that, the reaction between carbon dioxide and amines decreases the amount of carbon dioxide technically dissolved because it has chemically reacted with the solvent. Hence, a larger amount of carbon dioxide can dissolve because it takes a longer time to reach its saturation point. Finally, harmless gases such as nitrogen flow out of the tower, while the carbon dioxide-rich solution is fed into a stripper tower. This tower has a very low pressure and high temperature, which helps decrease gas solubility. Hence, a hot carbon dioxide-rich stream forms at the top of the tower, where it is transported elsewhere to be stored, while the purified amine solution flows back into the absorber tower through a pipe on the bottom. Cryogenic separation. Flue gas is passed through a molecular filter made to trap water vapor and trace gases such as sulfur dioxide, resulting in a gas stream composed of primarily carbon dioxide and nitrogen gas. This filtered flue gas is then cooled to approximately minus 120 degrees Celsius. This causes CO2 to deposit while nitrogen gas remains as a gas because nitrogen freezes at a much lower temperature. The solid carbon dioxide collects at the bottom of the container and is transported elsewhere to be stored, while the nitrogen gas flows out of the mechanism. Physical adsorption filter for carbon dioxide. This filter is made of a porous and polar adsorbent material that is exposed to the air or flue gas that traps or lets molecules pass through based on size, polarity, and shape. So, how does it trap carbon dioxide? Well, the linear or straight shape of carbon dioxide allows it to enter the pores really easily. Beyond that, again, the filters are made of a polar material that attracts carbon dioxide due to its polar bonds. Now remember, the whole molecule itself is nonpolar because both of its double bonds pull in opposite directions. To be scientific, carbon dioxide has a large quadruple moment, which simply means that there is a large and unequal charge distribution. Pretty simple. Finally, these filters have pores that are only slightly wider than a carbon dioxide molecule, so it interacts with the inner surface of the pore a lot, which leads to more electrostatic forces between the filter's surface and the carbon dioxide molecule as mentioned earlier. This traps it. Regarding my model, it involves a life-sized physical adsorption filter with 3 example molecules. We will test if the molecules get captured or not. I made the filter by attaching cardboard cylinders into a shoebox and taping magnets inside the cylinders to reflect the polarity of real-life filters. Beyond this, I made the propane molecule with a modeling kit, the carbon dioxide molecule with metal sticks and paper, and the hydrogen molecule out of small black and white pieces. Here is the propane molecule, here is the hydrogen molecule, and here is the carbon dioxide molecule. This model will test if molecules significantly larger than carbon dioxide, such as propane, do not get captured in the pores because they cannot fit into the pores. Molecules significantly smaller than carbon dioxide, like hydrogen, do not get captured in the pores because of their equal charge distribution and because they have very little interactions with the polar wall because of their small size. In light of this, diatomic molecules have very weak London dispersion forces because they have very weak intermolecular forces. And finally, a carbon dioxide molecule will get trapped because of its unequal charge distribution and large area of contact with the filter wall. This leads to many electrostatic forces forming and thereby trapping it in the pore. Well, let's test it. So, the propane molecule would not fit into the filter and did not get trapped, while the hydrogen molecule would not get trapped and went right through the filter due to its small size limiting surface area and lack of ability to attach to the magnet. However, the carbon dioxide molecule did get trapped because of its large contact with the filter, aided by its linear shape and its polar double bonds, which stuck to the magnet. Overall, this model taught me exactly how size, polarity, and shape influence molecular filters. For example, carbon dioxide's linear shape allows it to enter real-life filters very easily, just as it was very easy for me to insert the molecule into the filter. Also, it made me realize that molecules with a similar size, polarity, and shape to carbon dioxide would get captured as well in actual filters. Further research shows that water, or H2O, can get caught in these filters as well due to its similar size and polarity. It does not have the same shape, however. So overall, what can you do to help our planet with this information? Other than educating others and going out on the field to teach others about this amazing technology, not much. But you can donate today to the Environmental Defense Fund, which is a large non-profit committed to the fight against climate change. Will you create the change that becomes the light at the end of the tunnel? Only time will tell.